In the world of advanced manufacturing, there's a race going on. It's this silent, super high-stakes competition, and it's not fought on some racetrack, but in the most advanced factories and labs on the planet. This is the race for the perfect form, the flawless shape, and today we're going to take you right to the front lines of this incredible battle. Okay, so let's just dive right in. The question seems so simple, doesn't it? How do you create the perfect shape? But when perfection is measured in microns, and a single tiny flaw can mean the difference between success and catastrophic failure, well, this question becomes one of the toughest challenges in all of engineering. And we're not just talking about any old products here. We're talking about industries where precision is absolutely everything. Think about an airplane wing, a car chassis, a life-saving medical implant. In these fields, getting the shape perfect isn't about looking good. It's about performance, it's about safety, and sometimes it's literally a matter of life and death. So yeah, in this world, you just can't afford to make mistakes. But there's a problem, a huge one. When you try to shape metal into these complex, perfect forms, you're not just fighting against physics. Turns out, you're fighting against the material itself. You're fighting an invisible enemy. Okay, so let's meet the first villain in our story. It's called springback, and really, it's just the metal's stubborn memory. You bend it into this perfect curve, you hit it with thousands of pounds of force, and right when you think you've got it, it stubbornly springs back, ever so slightly, right back toward its original flat shape. So frustrating. The next enemy is way more subtle, kind of sneaky. It's called material thinning. See, as you stretch and pull the metal into its new shape, it can get dangerously thin in certain spots. It's this silent weak point, right? A hidden vulnerability that could compromise the entire structure down the line. And finally, you've got these things called geometric deviations. These are the tiny, almost microscopic imperfections that veer away from the digital design. To your eye, the part might look absolutely flawless, but these tiny errors can multiply under stress and eventually lead to catastrophic failure. So for years, engineers have been battling these enemies with these massive, incredibly expensive dies and molds. But what if there was a better way? What if a new hero could enter the fight? Something more flexible, smarter, and way more efficient. Well, it's called Single Point Incremental Forming, or SPIF for short, and it's a total revolution in manufacturing. Instead of some massive, costly die, you use a single, simple tool. And this tool moves across a clamped sheet of metal, almost like a 3D printer for metal, just progressively shaping it layer by layer. It's flexible, it's cost-effective, and it is perfect for prototypes and custom parts. But even heroes can get an upgrade. For all its strengths, SPIF can sometimes struggle with really complex shapes. So it evolved. It became Two Point Incremental Forming, or TPIF. This version adds a second support tool on the other side of the sheet, and it moves in perfect sync with the main tool. This gives you way more control. It cuts down on those pesky geometric inaccuracies, and it just boosts the whole process. So our new hero is powerful, for sure, but it's not invincible. Those enemies, springback, thinning, deviations, they're still there, hiding in the microscopic details. So how in the world do you fight a flaw that's way too small for any human to see in real time? You assemble a team of specialists. First up, you need a lookout, and that lookout is machine vision. This is an automated system using super high-speed cameras and intelligent algorithms to just watch the process unfold. It is the team's eyes constantly on the lookout for trouble. And the power of this tech is just astonishing. We're talking about superhuman accuracy here. Machine vision can spot splits, cracks, and surface flaws instantly. Defects that a human inspector might totally miss even after hours of careful work. Okay, so our lookout can spot problems, that's great. But how does the tool even know where to go in the first place? How do you give it a perfect map to navigate this complex, three-dimensional landscape with absolute pinpoint precision? For that, you need the navigator. That's 3D reconstruction. We're talking technologies like laser scanning and photogrammetry that create a perfect digital twin of the part. This isn't just a blueprint. It's a high-fidelity, ultra-detailed map that allows for flawless toolpath planning. It makes sure the tool follows the intended geometry right down to the micron. All right, so now we've got eyes and we've got a map. But the battlefield is always changing, right? The material might behave in unexpected ways. So how can a system learn to predict these changes and, this is the important part, adapt to them in the middle of the fight? This is where you bring in the mastermind, artificial intelligence. Using these complex neural networks that are trained on massive amounts of data, AI can actually predict how the metal is going to react. It learns from every single pass of the tool. It anticipates problems like springback, and it optimizes the entire process on the fly. It is the brains of the entire operation.
So, what happens when you let the mastermind take charge? I mean, what kind of crazy precision can this team actually pull off? Well, the research gives us this one incredible number, plus or minus 0.175 millimeters. To put that in perspective for you, that is about the thickness of 2 human hairs. That's the level of mind-blowing accuracy we're talking about when this whole system works together. Wow.
So, with our hero chosen and the team assembled, the mission's final phase can begin. We are right on the cusp of a fully automated future for manufacturing, a future that's built on data, on intelligence, and on just unbelievable precision. The ultimate goal here is something engineers call a closed-loop system. This is where the whole team works in perfect harmony. The lookout spots a tiny deviation, the navigator instantly updates the map, and the mastermind immediately corrects the tool's path. It's this continuous cycle of feedback and adjustment, happening thousands of times a second, all in the pursuit of perfection. To really get how big a deal this is, it helps to see how it builds on centuries of progress. I mean, we went from the skilled hands of ancient metalsmiths to the computer-controlled precision of CNC machining, then to the flexibility of incremental forming. The next logical step, the one we are entering right now, is fully automated, robot-assisted forming, all guided by these incredibly intelligent systems. The researchers behind this work really put it perfectly. This integration, this teamwork, it isn't just about making parts more accurate. It's about opening up entirely new possibilities for what manufacturing can even be. Smarter, faster, and way more creative than we ever thought possible. And that kind of leaves us with one final, fascinating question to think about. When this race for the perfect form is finally won, when our tools can create any shape we can imagine with near-perfect accuracy, what new things will we be inspired to build? What amazing challenges will we solve? The possibilities really are limitless.